Find the maximum value of z. In this problem, the objective function, z, equals 2 times x1 plus 3 times x2. The constraint set includes decision variables x1 and x2, both of which must be non-negative. The problem also states it should be solved graphically. Solving the problem graphically means sketching the feasible solution space using the constraint set and then determining the optimal solution in the feasible solution space using the objective function. The feasible solution space is comprised of the union of all constraints in the constraint set. Plotting out 4 times x1 plus 3 times x2 is at most 12. The feasible solutions for this linear constraint is shaded in yellow. The constraint of x1 minus 2 times x2 is at most 2 is sketched in, and the feasible solution for this constraint is shaded in green. Lastly, the two non-negative constraints are plotted and the feasible solution space is shaded in violet. The union of these three shaded areas is shown in orange and represents the feasible solution space. Since the objective function is linear, if the optimal solution is unique, it will occur at one of the 4 vertex points on the solution space. If the optimal solution is non-unique, it will occur along one of the 4 edges of the solution space. If we set the objective function value of z equal to a constant, say z equals 6, and sketch the line, we notice multiple feasible combinations of x1 and x2 can generate an objective function value of 6. Since we're seeking the maximum value of z, we trace additional parallel lines of constant objective function values in the direction of the directional derivative, without exceeding the feasible solution space. As it turns out, the solution of x1 equals 0, x2 equals 4 is the optimal solution, which would generate an objective function value of z equals 12. When reviewing the possible solutions, the answer is A. We can check our solution by evaluating the objective function value for all 4 vertex points. Substituting in the decision variables into the objective function for each vertex point, we can solve for all objective function values and confirm 12 is the maximum. If we were to solve this problem using the simplex method, with slack variables s1 and s2 in our initial basis, the 2 non-negative constraints would be active. From pricing out, x2 would enter the basis, and the slack variable associated with the first constraint, s1, would become non-basic. Now, the first constraint would be active, and x2 would be greater than 0. After pivoting, we would realize this current solution of x1 equals 0, x2 equals 4 is the unique optimal solution. Linear programming problems with more than 2 dimensions can be visualized the same way, although they cannot be easily depicted in a plane.